Welcome. I'm Andrew Berns, an assistant professor of computer science at the University of Northern Iowa, and I'm here today to present my paper for SSS 2021, Applications and Implications of a General Framework for Self-Stabilizing Overlay Networks. Diving right in, what exactly is an overlay network? Why do we care about this problem? What's our motivation? Overlay networks are networks where communication happens over logical links. These logical links consist of zero or more physical links. The benefit of that, of using the logical links instead of the physical links, is it allows us to basically to simulate or to logically be directly connected to various devices that we may be physically quite removed from. Because the connections happen logically, I am allowed, or our algorithms are allowed, to actually modify the topology by adding and deleting edges. Right, so the typical example of an overlay network would be the internet. Even though my computer stays connected to my router here at home, when I type in google.com, it is as if I'm making, connected to Google's server. There is a logical link between my machine and Google's machine, and that's a typical, or the quintessential overlay network example. Now, the reason we might want to build these is that they take, what is probably a very disorganized physical network, or at least less than ideal physical network, and lets us impose structure that we can use for things like being able to efficiently search for certain resources, being able to route messages between nodes cleanly, etc. So overlay networks give us the ability to add and delete edges to the network so that we can shape the network to do what we want. Now the question becomes, how exactly, what kinds of things can we build? And so in this paper, we're going to be looking at two questions and answering two questions. Number one, can we design robust algorithms to create particular topologies? So in this case, suppose this is the topology I want for my system, for my network. What kinds of algorithms do we have, or is there a general algorithm that we could use to build that particular topology? The second question we're going to look at is there something? What do I need to know to design a topology that can be built efficiently? So it turns out some topologies can't be built efficiently. Are there tips? What kinds of things do I need to know about a topology so that I can build it explicitly for the reason of it having efficient convergence, and then of course meeting my other application needs? So we're kind of going both ways here. We're saying, number one, we want to be able to build any topology that we want. And number two, we want to learn insights about how topologies are built so we can select a new topology to build that can be built efficiently. And that's what we'll be discussing for the talk today. In the overlay network model, we'll represent the processes as nodes on a graph, and we'll assume that we have lowercase n number of processes. Those processes will all have a fixed, immutable, unique identifier from the range of 0 to capital N. Capital N will represent then the maximum number of nodes I might have in my system. These nodes can communicate when there is an edge connecting them. Two nodes can communicate when there is an edge connecting them. We will assume a synchronous, reliable message passing model where any message sent in round I is received in round I plus 1. A standard approach there would be in a particular synchronous round, a node receives all of the messages that were sent to it in the previous round. It performs some local computation, and then it sends out messages to its neighbors at the end of the round. We will assume that the channels are reliable and have bounded capacity, meaning that a message is received by a node if and only if it was sent by a node from our algorithm in the previous round. So entirely reliable communication. Now, one of the fun things about the overlay network model is that beyond these standard distributed computing model assumptions, we are also allowed to modify the edges. Remember, communication happens over logical links. Therefore, I can add and delete these logical links using program actions. So these edges become part of a node's mutable state. If we take a look at this example, node 14 is connected to both node 3 and node 54. Node 14 could perform a introduction that would then connect or add the edge between 3 and 54, and now 3 and 54 are immediate neighbors. They went from 2 neighbors to immediate neighbors. Similarly, I can delete edges if I take a look at 5 and 93. If they both decide that they no longer need that edge, they can go ahead and remove it, and now they are no longer at distance 1 from one another. So both of those are legal operations that I can do in the overlay network model. Why do I want to add and delete edges? Well, for us, we'd like to make a self-stabilizing overlay network algorithm. A self-stabilizing overlay network is one that will guarantee to build correct or reach a correct configuration after any transient fault and remain correct thereafter. Frequently, we'll model this as the network starts in some initial arbitrary weakly connected configuration, and then it performs program actions, adds and deletes edges until it reaches a correct configuration. In this example, let's imagine that this network at the bottom is what the current state is, but this thought bubble, this dream, is what configuration it would like to be in the correct configuration. Remember correctness defined over the state of the processes, which includes edges, and so the edges of the network are part of the legal configuration. If this network were self-stabilizing, it could start from a configuration like this, and it would add and delete edges until it reached the desired configuration for it. So obviously a very strong fault tolerance model. These algorithms are pretty powerful as far as the ability to deploy in realistic settings or fault-prone settings, because as long as the fault is transient and you let the system run afterwards, it's guaranteed to build or restore the system to a legal configuration. When it comes time to evaluate these algorithms, we're going to be looking at 2 measures, one about time and one about space. When we're looking at the time, we're going to be thinking of what's called the convergence time, and that's just going to be the maximum number of synchronous rounds that are required for us to build a correct configuration, a legal topology, starting from any arbitrary initial configuration. So it's in the worst case, this is how long it will take for our algorithm to build the correct overlay network. And we're also interested in the degree expansion, which is a measure of the space complexity. Informally, it's basically how many edges our algorithm added that didn't need to be there. A little more formally, it's the ratio of the maximum node degree during convergence over the maximum node degree from the initial or final configuration. The intuition behind that is that if you start out in a configuration with a high degree, or you have to finish in a configuration with a high degree as part of the final configuration, then there's no hope of your algorithm keeping that degree small, and we shouldn't penalize our algorithm for that for those degrees being large when it's outside of our control. So the degree expansion is an attempt at getting at what is the extra edges, that is, what is my algorithm adding that is not needed at the final configuration. How big can my degrees grow? All right, now we move on to try to identify a general framework that we can use. To build this framework, we looked at a paper we had in 2015 called Avatar. In the Avatar work, we basically built a self-stabilizing overlay network for an embedded complete binary search tree. What I mean by that is on the left-hand side, we see a set of 4 what we'll call real nodes or host nodes. These would be the nodes in our problem. What we will do is we will embed onto this set of, in this case, 4 nodes. We will embed a 15 node, whatever our capital N is, 15 node, in this case, complete binary tree, so that it has a dilation 1 embedding. What that means is that every node will be able to, basically we make a sorted list then every node can use information about its successor and predecessor to determine what nodes it should be hosting, what virtual nodes it should be responsible for, and therefore which neighbors it should have to realize that dilation 1 embedding. So in this case, we take a look at 5, and we note that node 5 corresponds to 5, 6, and 7 virtual nodes. Notice virtual node 7 is connected directly to 11, the blue node, and so 5 and 10 should be connected to each other. The use of this dilation 1 embedding means that if you can define an overlay network with n nodes, capital N nodes, it becomes locally checkable when embedded on Avatar, which is a pretty important piece of it. Now, how do we build Avatar CBT? Well, it's a pretty straightforward divide and conquer algorithm where we initially cluster the nodes into groups. Each of these clusters represents its own capital N node target topology. So in the case of the CBT network, we had each cluster was could be thought of as a 15 node or an n node complete binary search tree that was embedded onto the nodes of the host network. So we cluster them into these groups. We then match clusters together so that we can have them merge and make a lot of progress quickly. So we match them and then we merge the matched clusters into a new single cluster. So we'll do this over and over and over again, this matching and merging until eventually a single cluster remains, and that single cluster will be the correct configuration. Now that's what we did for CBT, the complete binary search tree, but we did wonder, could this work for any target topology? So it turns out actually, yeah, if you look at the description of this algorithm, nowhere does it explicitly state that this is only for CBT. In fact, all we really need to get this to work for any target topology is a few different measures. Number one, we need to know the diameter of the target topology, which we'll represent as d t of n. This is going to be important because every time we do a match or a merge, it requires that we coordinate between nodes of two clusters. That coordination is done by sending messages through the cluster, which requires obviously order d to the tn rounds. So every time I do a match and every time I do a merge, it takes up order d to the tn rounds in expectation because there's some randomness in there. I would expect that each cluster then participates in log n merges before a single correct configuration is reached. That makes sense. Every cluster should merge with some other cluster in an expected d to the tn rounds, and so that should happen log n times. And what we end up with is if we take the algorithm, the cluster match merge repeat algorithm, it's actually will do any arbitrary target topology t with a convergence time of on the order of d to the tn times log n in expectation. So said in another way, if I have a target topology t that I'm trying to build, I can build that in log n times the diameter of my target topology. So you pick the target topology, boom, there's your self-stabilizing algorithm and the complexity, time complexity. How about the space complexity? The space complexity actually depends on something called the maximum degree of embedding. This is going to be what's the maximum degree any node may have from any subset of nodes to realize a dilation 1 embedding of T, at least as defined by Avatar, where you have your successor and your predecessor, and then you're responsible for all of those nodes in that range. There's a formal definition of it in the paper, and we can give some examples too. Again, it's just a metric of if you need a dilation 1 embedding, what's the largest number of external nodes, if you will? What's the largest number of neighbors a node may have even if it has a large number of guest networks. It turns out that during merges, that maximum degree embedding, that's a limiting factor on how big a node's degree will get. This makes sense because by definition, the maximum degree of embedding is the largest degree a node may grow in any sort of n node configuration. So then we only have to worry about what happens during the matches. It turns out that every time we do a matching step, the node's degree may increase by the maximum degree of embedding, but there are, in expectation, only log n matching steps. And so, again, if you can give me the target topology, I can then give you an algorithm that will stabilize and have a degree expansion of that maximum degree of embedding times log of n in expectation. So this is a pretty powerful idea that we can take the any target topology, define some metrics, and then discover or use those metrics to determine how fast or build a self-stabilizing algorithm and determine its performance. All right, and so we can go ahead and take a look at a couple of examples of using this avatar framework for general or for various target topologies, and then how those metrics would apply. For instance, the chord topology. This one is a little bit more interesting. Note that the diameter is order log of n because in every step I can have the distance to any other node thanks to the long distance links that are being displayed here. However, the maximum degree embedding is also order n. The reason that happens is in our embedding, what would happen is a host node might have to take multiple nodes around the ring. So I might host this node, this node, this node, and this node. Notice each of those 4 nodes has a long distance link. That is, each of those 4 nodes has a link that goes all the way across the ring. And so if I have, if the real nodes aren't uniformly distributed, I might actually be in charge of simulating or in charge of hosting a very large number of virtual nodes, and potentially up to order n. So on the one hand, chord is nice. Chord by itself is nice to put into our framework as far as runtime is concerned. It can build it in polylogarithmic log squared n, but the degree growth is enormous. Order n, which is the maximum the degree growth could be. Again, coming from the fact that the more nodes I host, the more long distance, the more nodes I host, the more nodes I have to be neighbors with, and my degree grows. So, we used this. Number one, we took our framework and we applied it on a couple of examples and said, yes, we could build, the chord network in a self-stabilizing fashion with this complexity. We could build CBT. We could build linear, and so those examples are contained inside of the paper. What's also inside the paper is actually a new topology that we designed based upon the insights that we gained by looking at this general framework. So at the beginning of the talk, we had kind of talked about a two-pronged approach to self-stabilized and overlay networks. We talked about we were interested in building algorithms that worked for a particular topology. We were also interested to see if we could design topologies that were amenable to efficient stabilization. And this avatar framework, it satisfies both of those. So if you can define a particular topology, then we determine the diameter and the maximum degree of embedding, and we can tell you, we have an algorithm. We can tell you the complexity time and space wise. Similarly, the insights that we gained from looking at this general framework. So the understanding that the convergence time is going to be determined largely by the diameter of the network. The identification of the maximum node or degree of embedding that has a big role in the degree expansion. And so in our paper, you can read about how we actually create a special type of network, a variant of chord called skip chord, which has efficient time and space convergence requirements. And again, these are all things that are possible thanks to the viewing it through this lens, this general framework of the avatar embedding. So with that, I'd like to say thank you very much for everybody for watching the talk. And also thank you very much for the program committee and the reviewers for SSS 2021 for your valuable comments. Definitely made the paper better. Your hard work is very much appreciated. Please let me know if you have any questions on the paper. My email address is given there, and I will show the references. And thank you again for attending.